For example, a brute force solution to the traveling salesman problem, where every possible route is considered, exhibits exponential growth. The time required to evaluate all the possible paths increases very quickly. Hello all, welcome back to Being Passionate Learner. I hope you all are doing well. This video is the second lecture on design and analysis of algorithms. Today we are diving into an important topic in computer science, which is growth of functions. If you are into algorithms or just curious about how growth of functions affect efficiency of an algorithm, this video is for you. But before we get started, if you are new here or haven't subscribed yet, hit that subscribe button and turn on the bell notification so that you will never miss any of my upcoming videos. I have planned the amazing contents for you. Now let's get started. These are the contents of the video. Why analyze growth of functions, common growth rates, constant time function, logarithmic time function, linear time function, quadratic time function, exponential time function, and summary. Let's begin with why analyze growth of functions. In computer science, analyzing the growth of functions is crucial for understanding how an algorithm performs as the input size increases. This analysis allows us to evaluate the efficiency and scalability of algorithms, which is essential for solving real-world problems efficiently. When we talk about analyzing the growth of functions, we focus on two main resources, time and space. By analyzing how functions grow with respect to these resources, we can design algorithms that make the best use of time and memory. In scalable computing, the ability to handle larger amount of data and more complex problems efficiently is essential. As input sizes grow, algorithms with poor growth rates will slow down dramatically, making them impractical for large-scale applications. Analyzing the growth of functions help us choose algorithms that can scale effectively, ensuring that our systems remain responsive and efficient with larger dataset or more users. Ultimately, analyzing the growth of function is about ensuring that our algorithms can perform well as the scale of a problem increases. It helps us build systems that are not only functional but also scalable and efficient, which is a key to solve complex real-world problems. Now let's discuss common growth functions in algorithm analysis. When analyzing growth of algorithms, it's essential to understand how different functions grow as the size of input increases. These growth functions represent the efficiency of an algorithm and are fundamental in choosing the right approach for a given problem. Let's explore some of the most common functions you will encounter in algorithm analysis: constant, logarithmic, linear, quadratic, and exponential. Now let's discuss this one by one. Constant time, big O of 1. The constant time function is represented as big O of 1. It means that the algorithm's performance does not depend on the size of the input. No matter how large the input gets, the algorithm will always take the same amount of time. Example, accessing a specific element in an array or performing a simple arithmetic operation. These operations are done in constant time as they take the same amount of time regardless of the input size. Logarithmic time, big O of log n. The logarithmic time function, denoted as big O of log n, describes an algorithm whose runtime increases at a slower rate as the input size grows. This happens when the problem size is halved at each step, making the algorithm very efficient even for the large inputs. For example, binary search is a classical problem of a logarithmic time algorithm. It works by repeatedly dividing the search space in half, so the time complexity grows much slower compared to linear algorithms. Now let's discuss linear time, big O of n. The linear time function is denoted as big O of n, meaning that the time complexity grows directly in proportion to the size of input. As the input size increases, the algorithm's runtime increases at a consistent rate. For example, a simple loop that iterates through all the elements of a list is an example of an algorithm with linear time complexity. The time it takes to complete depends directly on the number of elements to process. Next is quadratic time, big O of n square. The quadratic time function is represented as big O of n square, and it means the algorithm's runtime grows proportionally to the square of the input size. This can quickly lead to inefficient performance for large inputs as the time complexity grows much faster than linear. Example, a nested loop iterating through a list twice, like bubble sort, resulting in a quadratic time complexity. For each element, you compare it with every other element, leading to a runtime that grows significantly as the input size increases. Exponential time, big O of 2 raised to n. The exponential time function, denoted as big O of 2 raised to n, represents the algorithm whose runtime doubles with each additional input element. This results in a very rapid increase in computation time, making the exponential time algorithms impractical for large inputs. For example, a brute force solution to the traveling salesman problem, where every possible route is considered, exhibits exponential growth. The time required to evaluate all the possible paths increases very quickly. To summarize, constant time functions performance remains the same regardless of input size. Logarithmic time functions performance increases slowly as input size grows. Linear time functions performance grows directly with the input size. Quadratic time functions performance increases much faster as input size grows, and exponential time functions performance becomes impractical for even moderately large inputs. By understanding these functions, we can better analyze and choose algorithms based on how they scale with the input size, ensuring we make efficient choices for real-world applications. With this, we have reached to end of this video. If you found this video helpful, don't forget to like, subscribe and hit the bell for more algorithm insights. Thank you for watching, and I will see you in the next one. Till then, being passionate learner, keep learning.